So let's take a step back and see where we are. We talked about graph tasks in general, gave an example of constructing these histograms, talked about structural, traversal, and pattern tasks, gave PageRank as an example of both a structural and a traversal task, and then talked about pattern languages in Sparkle and SQL and Datalog, gave a few more detailed examples of Datalog motivated by what's been going on in the news in June 2013 related to the PRISM system. But what we haven't talked about is how to implement much of this, especially at scale. So that's what I want to do next. We're going to stick with Datalog for a moment and think about how to actually implement those kinds of queries in MapReduce, and then talk about how to implement PageRank in MapReduce. So way back towards the beginning of the course, we talked about how to implement relational algebra operations in MapReduce at scale, and we showed this sort of connection, between languages like Pig and the relational algebra. What databases do is obviously the relational algebra, and what you can implement directly in MapReduce. So there seems to be this kind of relational algebra DNA in a lot of these large-scale programming platforms. However, all of those cases, we never had anything that had to loop, that had to do recursion, that had to do iteration. And now that we're talking about graphs, as we sort of pointed out, that traversal of these graphs is really the salient feature of working with them. And so it came up in traversal tasks, and it came up in pattern languages in Datalog. We saw examples of recursive Datalog programs without talking much about how they would be implemented. So I want to cover that a little bit now. So given if you have a recursive Datalog program that looks like this, so you can say this is an edge relation that's just linking an arbitrary vertex x with an arbitrary vertex y. Every pair of edges is stored in a relation called edge. And I write this program. This program says, find me all the edges connected to the vertex labeled W, and here we have a vertex labeled W, and put those in a new relation called A. Then also find me additional values of A in this manner. For every vertex that's already in A, go find me an edge that leads out from that vertex and give me a new generation of vertices. So this is now a recursive Datalog program, but what you can think about it intuitively, what it's doing is traversing this graph in kind of a breadth-first way, right? So first we fire this rule, which just says, out of all the vertices, select the one with W. And we know how to do this. We could write this in SQL, I would hope. Right? We can write this in MapReduce. We could write this in Python. Find me all edges where the first position has a label equal to W. And call that A0. Or find me everything that's connected to W, call all those collectively A0. Next we go to this rule, and now we have to join all the ones we've already found with the edge relation to produce a new generation of vertices. For each node in A0, find all of its neighbors. And then in step 2, we fire this rule again. For each node in A1, find the neighbors, and so on. So we keep finding more and more vertices in this graph as we go one generation away. And that's naively how we might evaluate this recursive program. That's what the meaning of this program is. Okay. But there's a problem here. What if there's a cycle in the graph? Well, at generation 1 we'd find Sue, at generation 2 we'd find Tom, at generation 3 we'd find Lynn, and then in generation 5 we'd find Sue again, and so we would just keep going. So we need one more piece, which is to remove all the ones we've already found previously. So let's look at this again. So this is called semi-naive evaluation. So here's this reachability query that we were just looking at. Find me everybody that's connected to everybody that's in the social network of some vertex labeled A, right? Everybody that's reachable from A. So here's how it would work. We're going to have these delta relations, which are just just everything found in the new generation, right? Just like those colored levels were in the previous pictorial representation. So while we're still finding new vertices, we're going to keep going. If at any point we don't find anything new, then we know we're done, and we can stop and we can return the result. Okay, so while we're finding new things, let's call A to AI the union of all the deltas that we found previously. At iteration 0, union with iteration 1, union with iteration 2, and so on. And if you're not familiar with this notation, this just means, think of it as concatenation in a programming language, right? Except you're also going to remove duplicates. All right. Then delta AI is the previous new results joined with the relation R, right? So this gives me one more generation, and I'm expressing this in the relational algebra notation of join. So that's what we showed pictorially a moment ago. However, now what we also want to do is remove any duplicates. We want to subtract out anything we found in any previous generation at all. And this is in order to break cycles. If we've already seen that, if we already found Sue, then we don't want to find her again. All right. And then we increment this counter so that we can keep track of everything. And then our final result, when we're done, is this AI for whatever I is at the end. And so I'd claim that if we're going to do this in MapReduce, which is what we're trying to build up to, then this line is the important line. This line is actually pretty easy in MapReduce because of an implementation detail. A union of a bunch of different data sets, if they're known to be disjoint, is actually literally just concatenation of the files, which sort of happens implicitly in MapReduce. And I'm not going to go into much more detail than that, but suffice it to say that this line can be arranged so that it's not very expensive. It's essentially free. But this line is where there's a lot of work going on. So let's look at let's break this down and pretend like and show how this is going to be implemented in MapReduce. All right. So it's actually two different MapReduce jobs, one to do the join and one to do the difference. And we saw this in the lecture on pig, where join was one operation, and we didn't show a pig operation corresponding to difference, but you can implement it using grouping. Okay. But we did see that generally one operation and another operation would turn into two different MapReduce jobs chained together, and that's the same thing that's going on here. So what happens with the join is we have the delta A from the previous iteration, along with the very large edge relation, right? This is billions of edges, perhaps, spread across all sorts of computers. And we process them all in parallel, spray them across the network, and implement the reduce phase in order to compute the join. Then to do the difference, we find everything we just found from the join, spray it across the network again, along with everything that we've ever seen before, everything in this AI, everything in the union, and make sure to remove duplicates. And you implemented both of these things, or specified how to implement both of these things in the MapReduce assignment. You showed how to do a join, and you showed how to do a duplicate elimination, essentially, which is what this is doing. Okay. And then the only new piece we need, which is where MapReduce gets a little bit it becomes a little bit of a poor fit for this task, is that you need some sort of external driver program to control the iteration, to check and see if there's anything new. Okay, so MapReduce can't do loops in and of itself, so you have to do something outside of the system. All right. So again, two big steps: compute the next generation of vertices or nodes, and remove the ones we've already seen. All right. So this is fine, and this works, but there's some performance issues that are pretty significant, and we'll talk about that next time.